you're doing well today. Make sure that this is working. Let me know if it's too loud, guys. Hope you're doing well. Welcome to another rendition of Zephyr 101. This is Zephyr 101 summer version. You got the t-shirt. And yeah, we're going to be talking about debugging in Zephyr, particularly using the Cortex M debugging extension for VSCode. So we're just configuring that, getting it up and running. Some of the kind of nuances and the things you just got to know about when you're debugging on Zephyr. There's just some gotchas that will get you if you're not careful. So we'll jump in. And if you haven't subscribed, hit that like button, hit the bell icon, and subscribe. It'd be really great to see you here on the next one. So, and you won't get notifications unless you go if you don't click that notification icon. So let's go. So we're going to be talking about stepwise debugging. It's handy for figuring out what's happening inside your code. So I have used it for all types of different purposes, figuring out why a Stack Overflow is happening, figuring out issues with serial interfaces. So it's handy. I don't use it a lot, but when I need it, it's fantastic. You can use it to view the values of registers and memory at that point in time in execution. You can set breakpoints. So we can set them. The breakpoint essentially is a point where you can stop the execution, and then you could view values. You can kind of slow things down. So it's very handy for especially if you're working with something that's like time dependent. You can kind of slow things down, kind of click through execution of your code to see what the heck is going on. It's particularly also useful if when you're going into a fault handler, you can kind of see which instructions are causing you to jump into a fault handler. So that's just another great thing about it. We're using the, so this is something that I discovered. I'm going to zoom back out again. This is something I discovered recently is the RPi 2040. The Raspberry Pi Foundation actually developed a debugger that runs CMSIS. So CMSIS, I could just call it CMSIS DAP, and it runs the NR9160. And pretty cool is that the next version of the next product that's coming out of Circuit Dojo is the NR9161 Feather, and it will have a CMSIS DAP built in. So that's kind of exciting. I'm working through it right now, but I mean, literally, if you look at my screen again, I mean, it's running code right now. It's actually paused because I'm running the debugger, but it's actually running code, which is fantastic. It's programming it directly. I don't have any external debuggers or anything. So very, very exciting. One thing that you can do if you have other devices is, as long as it's supported by PiOCD, you can use the Raspberry Pi debug probe. Here's my setup. All you need is kind of an adapter board to go from a tag connect to the debugger, but that's the extent of it. And if you think about it, it's $49 for an NRF53 development kit, which is kind of the cheapest option besides a J-Link EDU. And now you can buy a debugger for $12 plus a little adapter board, and then the biggest thing is just the tag connect, and that'll be going away. So you got some options out there. It helps folks with issues on cost. So let's keep going. So the biggest thing is having the Cortex Debug extension installed on your VS Code. That's kind of the minimal thing that you need here, and then you need to configure your launch.json. So this file lives inside your repository, your Zephyr repo. It's at the base of it, so at the root of it. So it lives right next to your Zephyr folder and your application folder and so on and so forth. So if it doesn't already exist, you can create a make directory vs.vscode and then create this launch.json. A lot of times, if you've been using VS Code with your repository, it'll create that .vscode folder, so it's already done. But you might not have that launch.json. Minimally, you need to create a configuration for the debugger. So this JSON is telling the debugger when you're in the graphical interface, like what ELF to use, what server to use, where you're going to get your GDB server, where it's coming from. A lot of the times, if things are included in your path, you don't have to go as detailed as this, but because this couldn't find my PyOCD install, and also it didn't really know where the toolchain was, I needed to provide that information. So make sure, so your executable, that anything highlighted here is the actual variable name inside the JSON. So executable needs to match the path of your Zephyr.elf. Actually, I think I did the full path, or I used the workspace route, and then the rest of it, the rest of the way there. You need to indicate the device type. So in this case, the NRF9160_XXAA, that works for both the NRF9160 and the NRF9161. I've tested it. It might also work for the NRF9131 and the NRF9151, but these are all things I have not tested. And the NRF9151 is in limited supply. I know they're out there though. Make sure if you're having issues accessing. So when I first started playing with it, I noticed it was getting an execution error. Turns out that just the debugger could not, or the extension couldn't find my PyOCD implementation, or the PyOCD executable. So make sure that is set. Setting full paths rather than relative ones will probably save you a lot of headache as well. And then setting the ARM toolchain path just to the place where the ARM Zephyr UBI GDB is, I believe. Let's see, is that in here? Yeah, it must know that the GDB is in there. So having the correct launch.json is critical. It might take some tweaking for your particular installation and setup. So that's probably the biggest hurdle of getting over, is just getting that working. I remember the first time I ever did that. I was like debugging NR52 or something, and I just couldn't figure it out. And it was just a matter of changing a couple of variables in the correct way. A lot of this stuff is fun, you know, especially when it's not working. But when it works, it's great. One big caveat, and this is kind of an important thing that I run into, is because if you have a bootloader installed, so if you have MCU boot compiling alongside your application, what happens is it runs as execution and then it jumps to the location of your application. The debugger, as far as I can tell, and maybe some of you guys are, I mean, all you guys are smart, but if you've had experience getting the bootloader working alongside debugging for your application, please, I'd love to know how that's possible. But typically, I will remove the bootloader from the hex file, so everything starts at the address that the bootloader starts at. That's just the best way I've found to debug applications. The cool thing about this is that you can leave the console open. So if you have a UART console, in this case, there's UART console built in along with the Raspberry Pi debugger, so you can do both of these things kind of in parallel. The nice thing is you can just leave it open. With the NRF9160 Feather, originally, if you wanted to load code, you had to have to close the console, load the firmware, open the console back up. Kind of a pain in the butt. So this way you can kind of look at everything at the same time, and you don't have to keep fiddling with it. You can flash, and it doesn't matter. Speaking of flashing, if you do make changes, so let's say you make some changes and you build a new ELF, and then you try to debug, it's not going to work because it won't line up with everything that's on the binary that's running on the device. So make sure if you do rebuild, you do need to reflash it before you debugging. So stop debugging, build it, flash it, and then load it back up. I believe even with this particular instance with PyOCD, it will load the binary to the device just to make sure it's the right version. So simply, once you have everything installed and configured, you have the left-hand side there, you have a little bug in the play button. You can go and hit that play button next to the Cortex Debug option, and it should fire everything up for you. It should open up the GDB server, and it should start running. In this case, when I first started it, it actually stopped at that line 560, the test start. So what I did is I just I created a breakpoint. So the breakpoint is that top arrow. You can click next to the line numbers, and it'll actually create a breakpoint for you. If you look in the bottom left-hand corner, that shows you the list of all your breakpoints. So that's pretty cool, pretty handy. And then you can see the output. So I've started the execution and it stops after sending out that log. So you have the output of that log at that lower arrow. You can see that test start. So that's, it's working. It's great. One thing that I did also, just to kind of get like a reoccurring task, because I put in the blink function, I put a breakpoint at the reschedule function. So every time the LED was toggled, it would actually stop in that work queue and just wait for execution and for me to continue the execution. So it's just kind of like something you can play with if you're unfamiliar with debugging. You can put breakpoints in different places. You can actually jump into other files, the Zephyr code, to actually put breakpoints in there as well if you need to. It should continue to work as expected, but I have debugged some drivers and things like that way, especially like I mentioned before with serial interface. Debugging those type of things is really tough, especially if you have a lot of traffic on the devices. Maybe you're sending a lot of data back and forth, or you're doing a lot of requests. You can kind of slow it down and go like, all right, am I making the right requests? Or the data what I expect? Using like a SAILI. So along with using a debugger, I'll hook this guy up to the actual UART pins or I2C pins or whatever, and then kind of slow it down and see what the results are. And then obviously, and then make changes if there are issues with that serial protocol. Another awesome thing about it is that you can view registers. You can view global, local, and static variables. So in that left area where that arrow is, you can see the registers here. Might not be so useful for you depending on the situation, unless you're writing some custom code to actually use those registers. Typically, that stuff is handled by the compiler, so you don't necessarily want to mess around with the those registers. But the biggest thing is like figuring out variable values and things like that. You can also see that that error value, and it's optimized out. It's basically saying, hey, this thing's not really being used right now. You can actually, if you enable the Cortex or the config_debug and you set that to yes, it will not optimize out things like that. So you can actually see the value of that when you're executing your code. That's another. Usually the size of the application gets bigger, but it's just another thing you can actually turn on if you need it. So. And then you can see the static variables here. These are just living at the top of the main file, I believe. So biggest things is when you first set it up and start running, your execution may stop, or you have to set some breakpoints to actually see what's going on. It might actually continue. Once you start it, it'll just continue running. It really depends on your situation. And then, yeah, otherwise, if you have breakpoints set, that's the debugging will be using those breakpoints. Breakpoints are used to stop the debugger or stop the execution of your code to see, okay, I'm stopping here for you to review whatever you need to review, or if you need to look at a logic analyzer or whatever. So very critical. And I use that, for example, I use that breakpoint in the blink reschedule function to like stop, and I could do something, and then I could resume execution, and then it would stop again. It's really dependent on what you're using a debugger for. So, and of course, like I mentioned before, it's very useful for debugging any type of serial, something that's going way too fast for human, in a way that a human can understand, to slow it down so you can actually look kind of bit by bit and see what's going on. So we went over using VSCode, installing the Cortex Debug extension. We configured to launch the JSON in the .vscode folder. We are familiar with breakpoints to stop the execution, inspecting variable values, so variables, registers, and static, local, and global variables. And then, of course, you can use the console. And that's one thing. If you go back here, you can see in the middle there, in the terminal, you can actually see the output of that code, of the rest of the code when it's executing. And then one thing I didn't mention is that on the top right, you can see that bar. You got like the little rotated icon, kind of like the go back, and then you have the play button with the line, and then you have the jump over. All those are the controls for debugging. So if you're not familiar with debugging, play with the controls and just see which one does what. You can actually, I think you can highlight over, or you can hover over them. Yeah, you can hover over them and they will tell you what they are, and then it'll also tell you what the hotkey is. So if you're into hotkeys, you can actually do that. So like hotkeys for this, you got reset device. There's no hotkey for that. Continue is F5. Step over F10. Step into F11. Shift F11 is step out. Restart. Control Shift F5. Stop. Shift F5. So if you're not familiar with debugging, then get familiar with those controls, because that's the way you're going to control debugging along with breakpoints. So, all right. And I think that's it. Those are kind of a quick one. Hey, Scott. How's it going? But, yeah, very exciting. So, if you haven't already, jump on my mailing list at jaredwolf.com. I send out emails, especially when these live sessions are about to happen. So if you're not living on YouTube, you can at least get it in your inbox. Just an option. And I generally only send stuff out when it's important or it's of value to you guys. So join me there. But let me see if any questions. So Akos is asking, does the Raspberry Pi debug probe have any advantage compared to flashing debugger image in regular Pi Pico? So I think Akos is what you're saying is, if you have a regular Pi Pico, like I don't have one here, but one of the development boards, you can actually load the SWD, the Seamsys DAP firmware to one of those, and you can use that as a debugger. Honestly, I prefer just to get one of these guys because it's purpose-built hardware that it has some other functionality in it that makes it really nice just for connecting and debugging any of your ARM-based projects. So it has its own console port, and it has its own SWD interface. So I've essentially used that same circuitry and miniaturized it and placed it on one of these feather boards. So that's what's built into it. So it depends on what you have. If you are, I mean, it's $12. It's super cheap. But if you already have a Pico and you don't really want to buy a debugger per se, you can hook it up and save $12. For me, it just made more sense to buy a bunch of them. I'm going to be using them for factory and all this other things. So, whatever works best for you. I'm not here to judge. It should work though. It's awesome. It's very cool to see on a $2 chip you can put in a debugger and it just works. It's great. Cool. I don't see any more questions. But if you guys do have questions, leave them in the comments below, or you can jump over to community.circuitdojo.com, and I try to answer your questions there as fast as possible. I know some people are working on stuff live and they need help and they get stuck. So I try to help where I can. By no means, I'm kind of more of a Nordic guy. So if you come to me like, oh, STM32, it's like, I might not be able to help. Depends on how nuanced the question is. So keep that in mind. Cool. Sounds like your question got answered. Awesome. Cool. Well, thanks for being here on this Friday. Some of you might be melting from the heat. I know it's very hot here. So stay safe out there, stay hydrated, and we'll see you on the next rendition of Zephyr 101. Bye.